Today, I'll show you an experiment on input characteristics of transistor in C configuration. So before conducting this experiment in Proteus, I will explain what are the different configurations available in a transistor. This is a junction transistor. In any junction transistor, there are three terminals available, emitter, base, and collector. So these three terminals, I am representing by emitter by E, base by B, and collector by C. And in any circuit, one of these terminal, either emitter or base or collector, it has to be common for input circuit as well as output connection. So this part is input connection and this part is called as output connection. So one of the terminal has to be common for input terminal and output terminal. So based on this, there are three configuration. If emitter is common, see here, the emitter is common to input and it is common to output. So such type of configuration is called as common emitter configuration. If you make base as common, see here, the base is common to the input circuit and to the output circuit. Such configuration is called as common base configuration. If collector is common, this is collector, base and emitter. Collector is common to input terminal and output terminal, and such configuration is called as common collector configuration. But today I am showing you common emitter configuration. So this common emitter configuration is one of the most widely used transistor configuration in electronics due to its desirable characteristics. In this C configuration, emitter terminal of the transistor, it is common to input. Input is base emitter and output is collector emitter circuit. Collector emitter circuit is output circuit. Base and emitter circuit is input circuit. Between these two circuit, emitter is common. So the emitter is the reference for both input and output signal. Here the input signal flow and here the output signal flow. The input signal is applied between base and emitter, and the output is measured between collector and emitter. So this circuit I am going to construct using the Proteus circuit. So in this circuit, I need to measure the base current, I need DC ammeter. To measure the voltage between base and emitter, I need voltmeter, DC voltmeter. To measure the voltage between collector and emitter, I need another voltmeter. To measure the collector current, I need DC ammeter and one power supply, variable power supply on the output circuit and one variable power supply in the input circuit. I can't have the variable power supply directly in a Proteus. So this variable power supply is I can construct using a DC voltage source and a pot. So how to make the variable power supply in Proteus, that video already I have done. You go through that, you will come to know how to construct the variable power supply using DC power source and a potentiometer. This output characteristics. The output characteristics of transistor represents the relationship between VCE, output voltage versus output current. Output voltage is VCE, output current is IC. It is the relationship between VC and IC where we should keep the input current constant. Input current is IB. So output characteristics is nothing but relationship between output voltage VC versus output current IC, keeping input current IB constant. So it works in three different regions. So this is the output characteristics of transistor in C configuration. So here the plot on x-axis we take VCE, y-axis IC, and we'll keep the IB current constant. It operates in three regions. This is active region. This is saturation region, and this is cutoff region. Below the red line, it is a cutoff region. Above axis and below the red line, it is cutoff region. So in active region, in this region, the transistor operates as an amplifier. So only in active region, the transistor operates as an amplifier. So as the output voltage VCE increases, here the output voltage VCE increases, the collector current IC remains almost constant for a fixed value of base current. See, for look here, for when IB equal to 70 microampere, the IC current is almost constant as we increase the VC voltage. Similarly, when IB is 60 microampere, again the IC remains constant. When you keep IB at some fixed constant value, and the IC current remains constant, this region is called as active region. Okay, so in this active region, the base emitter junction is forward biased and collector base junction is reverse biased. If the transistor is acting as an amplifier, the base emitter junction must be forward biased and collector base junction must be reverse biased. This is all about active region. Now we will talk about the cutoff region, this region, below region. The cutoff region occurs when base current is zero or below zero or negative. When base current is negative, transistor operates in a cutoff region. It means in cutoff region, both the junctions, base emitter junction and collector base junction, both are reverse biased. In the reverse biased mode, transistor does not conduct. It acts as an open switch. So because of open switch, the collector current is almost zero. So the transistor acts as an open switch in a cutoff region. Then what about saturation region? So in saturation region, both base emitter junction and collector base junction both are forward biased. In this region, both are forward biased and the collector current is maximum. So in saturation region, the transistor acts as a closed switch. In saturation region, the transistor acts as a closed switch. Both the junctions, base emitter junction and collector base junction, both are forward biased. In cutoff region, transistor acts as a open switch. Both the junctions, base emitter junction and collector base junction, both are reverse biased. In active region, base emitter junction is forward biased and collector base junction is reverse biased. In this way, the transistor operates in three regions, so that you can observe in the output characteristics of transistor in a CE configuration. So this is all about the output characteristics of transistor in CE configuration. Now we will do an experiment using Proteus. So this is all about the introduction of common emitter configuration. Now I'll show you how to conduct an experiment in Proteus using common emitter configuration. So you should click on the Proteus software. So create a new project. Okay. Give the name of the project as input characteristics of transistor. Okay, click next, finish. Okay, next. So I need, what are the components required? You just say, I need BC107 transistor. Go here, find the device here, BC107. BC107 bipolar silicon transistor. Click OK. Place somewhere here. Okay, this is my BC107. And what you need, I need 1 voltmeter and 1 ammeter to the base. virtual instruments, click on DC ammeter, place here, and you need one DC voltmeter. Click here, and you need another voltmeter and ammeter on the output side. You need another DC voltmeter. Place between collector and emitter, and one ammeter, DC ammeter, I'll place here. Okay. So here in the circuit, this side should come positive and this side should come negative. So you click here, Y mirror you do. So Y mirror means, sorry, X mirror. X mirror, this side becomes positive and this side becomes negative. And the base current is measured in, this you write as IB. And the base current is measured in microamps. And output current is collector current, and it is measured in milliamps. Okay. Now what you need? I need 1 kilo ohm resistor at the base. So go to the component mode, pick component, resistor. Click generic resistor I am taking, click OK, and place here. Okay, the value of this should be 1 kilo ohm. Right click on this and change the property 1 kilo ohm. Now what I need one regulated variable power supply. So you go and V source you type. V source. Okay, click OK. I'll place here. And I want to make this as a variable DC power supply. I need a pot. Type pot. So here you will get pot HZ, you select. It is highly granular interactive potentiometer. Click OK. And place the potentiometer here. And on the output side also you need one potentiometer. I'll bring this side. Okay. And I need one DC V source also on the output side. Okay. Now your work is to join all the things now. So first join the microammeter to base, register to ammeter, and one end of potentiometer to DC voltage source, another end to potentiometer, and the wiper of the first potentiometer to resistor, and this should be connected to ammeter, and voltmeter between base and ammeter, and collector should go to ammeter negative. You check here, collector is connected to ammeter negative, and this should be connected to wiper. Okay, and this should be connected to positive of DC source, and negative of DC source should be connected to another terminal of the wiper potentiometer. And I'll bring this down, and this should be connected between collector and emitter. Okay. Next, I need one ground. Choose ground and connect here. Okay. Now everything is ready. So here I'll increase some voltage. Edit property. I'll keep this at 5 volts. Let input be 1 volt because I can get many values in terms of a 0 0.1, 0 0.2, 0 0.3 like that. So plot the output characteristics of transistor in C configuration. First, we should keep the IB current constant. To keep the IB current constant, first I'll turn on the simulation and increase the steps of pot and adjust the required amount of IB current. Here I'll keep the IB current I'll fix the IB current 25.2 microamps. Exactly 25 microamps I'm not getting. 25.2 microamps I'm getting. So open the Excel sheet and here you write the current is 25.2 microamps and write the two columns VC and IC for one set of reading and the other set you can fix some other IB value and again note down VC and IC current IC in a milliamps. Okay, now current is fixed. So with the help of this pot, vary the VC voltage and note down the IC current. For 0, current is minus, it is almost 0. For 0.04, it is 0.12. For 0.04, 0.12, already I have written in order to save the time. Next step, for 0.09, it is 0.22. 0.09, 0.22 current. Next step, for 0.14, 0.25, 0.14, current is 0.25. 0.19, 0.26. 0.19 I have not written. Next, 0.24, it is 0.26. 0.24, it is 0.26. 0.29, 0.26. Now it is almost remaining constant, 0.26. 0.33, 0.26. 0.33, 0.26. Current is almost remaining constant. 0.43, 0.26. 0.43, 0.26. 0.52, 0.52, 0.26. And last step I will take 0.62, 0.26. So these many readings I have taken. Next, I'll change the IB current to some other value and I'll repeat the same thing. So you bring this pot to 0 and increase this step. Earlier I kept 25.2. Now I'll keep 29.6. Note down here 29.6. Repeat the same procedure. 29.6. For 0, it is 0. 0.04, 0.15. 0.04, 0.15. Next, 0.09, 0.3. 0.09, 0.3. 0.09, 0.3. 0.14, 0.36. 14, 0.36. Next, 19, 0.37. 0.19, 0.19, how much? 0.37. Next, 0.23, current is remaining constant. 0.23, current remained constant. 0.37. Next, in further steps, current almost remains constant. 0.28, 0.23 over 0.28. Current is remaining constant. 0.37. Next, 0.33, 0.33. Current is remaining constant. One more step I'll take. 0.37, 0.37. Current is almost remaining constant. Now I'll show you how to plot the graph. So first you should select the first set of readings, VC, VC and IC. Click on insert, click on scatter, click on scatter with, not this graph. This graph you select. So I'll get the waveform. So you can change the x-axis label, primary horizontal axis. This is VCE voltage. And in vertical axis, IC current. It is IC. And you can write the heading, output characteristics, output characteristics. Okay, so next, in order to take the second set of reading, right click on the graph, select data, click on add, series name, IB is equal to how much we are taking, 29.6, 29.6 milliamps, microamps, and X series, select the range, X is BCE. Okay. Next, Y series, select the range, click OK, click OK. So I'll get this way. So red one is IB is equal to 29.5 microamps, and blue one is 25.2 microamps. So this is all about plotting the output characteristics of transistor in CE configuration. In this way, you can take many sets of readings. IB is equal to one more current, and note down again VC and IC. In the same pattern, you can plot the graph. See, the current is almost constant for higher values of VC. Initially, the current increases. After that, the current remains constant.